Hey everyone, I'm jumping ahead a little bit again through the review section. So I've jumped to the next big spot where we're tackling radicals. So we talked about taking roots of perfect, nth roots of perfect nth powers. So square roots of perfect squares, cube roots of perfect cubes. And then we talked about what happens when it's not a perfect square or a perfect cube and how that can just be your number. Your number can have a root in it, and that doesn't mean that you're not done. That can be the answer. And now we actually want to take it one step further and see when we have roots that we can quote unquote simplify without getting rid of the root completely still. So I would say you're probably going to feel like the word simplify is debatable here, but it is the correct use of it, especially for the purposes of this class. Okay, so remember we have this formula. In general, multiplication and division play nicely with exponents and radicals, since those two are really the same thing, or radicals are exponents. One direction, they're the same. So as we work our way through here, we're going to come back to that. So let's just start from the beginning. We already know that the square root of 16 is 4. 4 is clearly, I would say to most of us, simpler than writing the square root of 16. I like it. No fancy symbols. So great, that's simplified, I'm convinced. The square root of 7, this is an example like, what was that, 1.1.3, wherever we were last with radicals. There's nothing you can do. The square root of 7 is the square root of 7. The only way you can change the appearance of the square root of 7, well, you can probably think of other ways, but the only one I can think of that you'd be tempted to do is to plug it into your calculator and get a decimal. That would be close to telling you what the square root of 7 is, but it doesn't have all the information. It's not perfect anymore. So if we want a perfect answer, what is the square root of 7? The answer is the square root of 7. Where it gets interesting is when we have numbers with factors, basically. Sometimes that gets interesting, not always. So the square root of 18 is a really good example because not only does 18 have factors, it happens to have a factor, here I'm going to think about my order really carefully, that's a perfect square. So 18 is 9 times 2. And looking back up to our property says, and we've done a little bit of this before, especially with our units, we were doing this mentally, you can split that up. So we're going to end up with the square root of 9 being nice, and the square root of 2, we're stuck with it. It's not a perfect square, it doesn't have any factors to separate out. We're pretty much done. This process is called extracting roots. So basically, we started with a square root of something that wasn't a perfect square, so it wasn't just a quick, easy one and done, but we still want to talk about simplify. And the idea with roots is they're simplified, statements with square roots or cube roots or whatever, they're simplified if you remove any possible perfect squares or cubes, depending on what your root is, and you make sure that there are no roots in the denominators of fractions. So this seems kind of arbitrary, and I'm actually a big supporter of the idea that rationalizing denominators, getting rid of roots in denominators doesn't really make a number better, but we do need the skill for other reasons, especially in calculus. We need to know how to eliminate roots from certain parts of expressions when we need to. So first off, not worrying about the denominator business, just worrying about if you have a number under a square root that has factors that's not prime, investigate and see if any of them are perfect squares. The most simplified statement here will be the one with the smallest possible number left under the root. Okay, so similarly, square root of 8 is, okay, so factors. 8 factors into 4 times 2. And you can even go further if you'd like. You've probably had to do these like prime factorization trees at some point in your life. If you want to get all the way down to that, you can. And basically what we're doing is removing pairs. Anytime you have two 2's, that's a perfect square. If you have 2 3s, that's a perfect square. But when the numbers aren't too messy, I generally don't think quite that hard. I just say, okay, is there a factor of 8 that's a perfect square? And we know our perfect squares. 1 doesn't really help us, so we'll skip that one. But 2 squared is 4, 3 squared is 9, 4 squared is 16, 25, 36, so on. We're looking for these. And often we don't get too far down that list when we're working on these problems, just because it gets really tedious and you can learn the skill without me putting, I don't know what, the square root of 121 times something in there. So factors of 8 that are perfect squares, 4. So we're going to say, okay, 8 is the same as 4 times 2. Again, note this is only helpful if there's a perfect square. So if you have, I don't even know what's a good example, the square root of 6. That does have factors, 2 and 3. None of them are perfect squares. So it's going to be just like with the square root of 7, where we say can't do any better. Here, I can do better. I can split off that square root of 4, say, okay, basically what I'm saying is I can remove a number from under the square root by taking its square root, which I think hopefully seems reasonable. So I can't take the square root of 8, but I can take the square root of that factor 4 and put it out in front. Sometimes when we're doing these problems, there's already a coefficient hooked out in front of the square root. So we just want to think about this as 3 times the square root. We'll work on the square root and then we'll deal with the 3 as needed. So, same question. Does 12 have any factors that are perfect squares? And I really usually just work my way down the list. And again, I'm being kind of lucky here. I must be being easy on myself. 4 is definitely a factor of 12. So I'm going to mentally say, okay, 12 is 4 times 3. Feel free to skip a step or two in the middle if you'd like to as you get good at this. I think that a lot of people get so they can say, okay, I'm going to take out a 4, it's going to be a 2. Whatever you need to show me, I'm not that worried about seeing every single step for these. When I split that up, square root of 4, again, don't write the extra step if you don't need it. I just want to make sure we start off with all the steps. So this is a 3 times a 2 times a square root of 3. And here's where I actually worry about that 3 out in front. What I've written down is completely correct, but I can simplify a little more now because I know that 3 times 2 is 6. So this simplifies to 6 root 3. Again, if you're sitting there thinking, that doesn't look any simpler, this is silly, I agree, it doesn't look any simpler, but being able to correctly move numbers in and out of roots is very important, so we're going to do it anyways. Okay, a few more of them. Man, I got crazy. Sorry for the long video, sorry in advance. Okay. So this one, same thing. I just want to make sure you're not freaked out when you have a negative out in front or a number out in front. And really that's what we have. Remember that root 160 over 8 is the same as 1/8 of root 160. So if you want, you can move that 1/8 out in front. Don't have to. I just like to point that out because that's one that a lot of people aren't that comfortable with. When I'm looking at root 60, I can start down my list. 4 is a factor of 160, but I'm spotting right away that there's an easy one that's bigger than that. 16 is definitely a factor of 160. So if you don't spot it right away, it's okay. I'll show you what I do, but I want to show you this way first. So try to find the biggest thing you can, but not a disaster if you don't. Okay, so we're going to mentally say, okay, square root of 16 I can do, that's a 4. Square root of 10 I can't do, so I'll just write it down. 1/8 times 4 is 2. That negative should still be hanging on. And then you want to ask yourself, I haven't been good about this so far because I gave us nicer ones to start with, do I have any more factors that are perfect squares? And I don't. 10 breaks down to 2 and 5, no perfect squares, but you should ask yourself that because we might have gone with my first statement that, oh, 4 is a factor of 160. 4 goes into 160 40 times. Okay, and if you did this, you'd end up with negative 1/8 times 2 times the square root of 4. And negative 1/8 times 2 is negative 1/4 times the square root of 40. And that's great, but it's not what we ended up with. Did I just do 4, 2. Okay, I think I'm good with it. Why do I feel like I'm not going to get the right number out of this? Might be doing something silly. Oh, I already see it. It's because 1/8 times 4 is 1/2, not 2. Okay, so the reason that it's not matching up is because we haven't gotten all of the perfect squares. So there's nothing wrong with what we just did, but 40 still has a 4 as a factor. So we can say, okay, negative 1/4 times the square root of 4 times 10, which is going to be negative 1/4 times the square root of 4 is 2 times the square root of 10. Probably going to be mad at myself later that I took so much room, which is negative 1/2 times the square root of 10. So should work out the same either way. It does take a little more writing if you don't find the big one, but that is not a crisis. It's much more important that you can think through this and find these perfect squares to extract than it is that you find the biggest one on the first try. Okay, so cube roots, I don't want to neglect them. So just like before, it's kind of good to have an idea in your head of, okay, what are the perfect cubes? 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. I kind of have 216 memorized. I don't always, but right now I do because we just saw it earlier. But I would say usually up to 125 is plenty. So if you can keep track of up to 5 or 6 cubes, you should be in pretty good shape. So 135, I'm not thinking 8 or 64 are good candidates. I'm not thinking 25 is a good candidate. So I really hope I did good problem making up and that 27 is a good candidate. So let's see, 27, I'm going to say times 5 to get the 100. And I think I like that, 27 times 5. Here, so let me write it down and then I will double check myself. 27 times 5. Okay, so 20 times 5 is 100 and 7 times 5 is 35. It looks good. Okay, and then the steps are very similar. We're going to take the cube root of the 27. We're going to take the cube root of the 5. The cube root of the 27 is 3. The cube root of 5 is what it is, and that's our answer. Okay, let me switch colors. These are getting all kind of mushed together. All right, 2 more. Long video, but I'm almost done. Okay, so perfect cubes that are factors of 250. Looking at my list, I think I want 125. So I'm going to say, okay, that's the cube root of 125 times 2. And the over 10 doesn't really bug me. In the problem 2 up, I moved it out in front. You can do that. You can make it a 1/10, or you just leave it in the bottom. That's fine. Either way is totally okay. So I've got the cube root of 125, and again, I'm back to writing out all steps, but feel free to skip some steps in here as you get comfortable. And the cube root of 125 is 5. Cube root of 2 is just the cube root of 2. And this is beautiful. I can go one step further. We talked about changing the appearance of fractions. We should be able to reduce fractions, make their denominators smaller, or make them bigger if we need to. When we're trying to simplify, we would be hoping to make them smaller, and in this case, I can cancel out a 5. So I get 1 times cube root of 2 on top. Don't need to write the 1. I get 2 on the bottom, and I love it. No, you cannot cancel the 2's. Doesn't work. That's the cube root of 2 over 2. The only thing you could do to try and combine those would be to say, okay, that's 2 to the 1/3 over 2 to the 1. And you could subtract exponents, but that would put the radical in the denominator, which is one of the things we're going to try to avoid for the purposes of our practice. Okay, last but not least, 4th roots. So again, the idea is that you kind of have an idea of some of these. The bigger the power gets, the fewer I expect you to know. So we should know quite a few perfect squares. We should know a handful of perfect cubes. Perfect 4th powers, I would hope it doesn't get very big. I do know that 2 to the 4th is 16, and I know that 3 to the 4th is 81. Do I know what 4 to the 4th is? 64 times 4, 256, I think. Anyways, I'm already too big for this problem, so I don't have to go that far. If I could scratch that out. I didn't really even need 18. I sure hope that 16 works, because that's the only perfect 4th power that could possibly be a factor of 48. As soon as you get bigger than the number under the root, you've gone too far. And it actually is. 16 times 3 is 48. So we have 9 times the fourth root of 16 times the fourth root of 3, which is 9 times, move my paper. Fourth root of 16 is 2. Fourth root of 3 is fourth root of 3. So last step will just be to go ahead and do that multiplication. 18 times the fourth root of 3. Okay, so extracting roots is what we're doing there. When you remove the perfect squares from under square roots or perfect cubes from under cube roots, extracting roots. So give it a try. Let me know if it gives you any trouble. We're going to do it shortly with variables. So you want to make sure you really get the idea of what's going on with numbers. Thanks for watching.